So today we're going to talk about the so-called fundamental theorem of projective geometry. What does it say? Well, what it basically says is that a projection is uniquely determined by specifying how it sends three collinear points to three collinear points. So if I tell you that there's a projection which sends some points A, B, C on some line to some points A dash, B dash, C dash on some line, then that uniquely defines a projectivity that does that. There's only one projectivity that does that. And this is really quite a claim if you think about it, because projectivities can be really complicated objects made out of sequences of thousands of perspectivities and all sorts of things. But this theorem claims that although there are lots of different ways to make such mappings, there's really only one such mapping that changes points in one such way, which is going to send 3 points on one line to 3 points on another line. And it really gives us a kind of simpler way to think about what projections are. Anyway, the proof is really quite straightforward, and rather than going at it directly, let's ask a different question. Let's suppose that we've got 4 points on a line, 4 distinct points in fact, A, B, C and X. And what we're interested in is for another line, which might be a different one or it might be the same one. Let's say that we, on this second line, well, I'll call it the second line anyway. Let's say that on the second line, we know where the image is, A dash, B dash, and C dash are of points A, B, and C under some projection. So the information we have is we have 2 lines. On the first line, we know where A, B, and C are. On the second line, we know where the image is A dash, B dash, and C dash are. Now the question is, where can the image X dash of X be on this second line? If we have some projectivity, could it be in different places? Could it be the case that there could be several different projectivities which map A to A dash, B to B dash, C to C dash, but don't necessarily always send X to the same place? Or is it the case, hence it is the case, that in fact the position of the image of X is already predetermined once we specify this information about A, B, C, A dash, B dash, C dash? So to think about this then, we're going to look at a particular way that we can do a projection from A, B, C, X to A dash, B dash, C dash, X dash. And we've looked at this kind of projection before, maybe with a bit different labeling, but it's quite elegant really. The way you do it, for a start, let's suppose that our 2 lines are distinct. So our first line has these points A, B, C, and X. Our second point has these... Sorry, let me say that again. Our first line has these points A, B, and C, and X. And our second line has these points A dash, B dash, and C dash. So to find this projectivity that puts the points in correspondence in the proper way, well, one way to do it is we're going to do this projectivity as a sequence of 2 perspectivities. The first perspectivity, well, firstly, we're going to have to make an intermediary line, a kind of halfway house between our starting points and our finish points. And to make this line, we can just look at the points, well, we can look at the point where A dash B and AB dash meet, that'll give us 1 point on this intermediary line. And we get another point by, let's say, looking at where AC dash and A dash C meet. So that gives us 2 points. We rule a line through those 2 points, and that gives us our intermediary line. And what we're going to do now is we're going to do 2 perspectives. One perspective is going to be using this center of perspective or origin perspective A dash to project A, B, C and X onto the intermediary line. And we'll call the images of those points G, N, M and Q respectively. Now the second stage is kind of symmetric. We're just going to do a second perspectivity, but this time, rather than doing the perspectivity from the center A dash, we're going to use the point A on our first line as our center of perspectivity. And then, as you can see, this second perspectivity sends G, N, M and Q to A dash, B dash, C dash and X dash respectively. So this is one projection which sends, so this is one projection from our first line to our second line, and one way of finding finding an image X dash of X. Now you might ask, okay, what happens if the first line and the second line are actually the same? What happens if we're doing a projection from the, what happens if A, B, C and X and A dash, B dash and C dash are all on the same line? Well, that's no problem. All we have to do is draw a line anywhere, and then we'll have an extra point O, and we'll start off by doing a perspective using center of perspectivity O, which is going to send the points A, B, C and X onto some points A1, B1, C1 and X1, which are on another line. And then we've basically got the same kind of setup as we had before. We have these points A1, B1, C1, X1 on a line, and we have these points A dash, B dash and C dash on a second line. And as you can see in the diagram, we just follow the same reasoning after that, and we get once again this projection, which then, so to cut a long story short, basically what we've said so far is that we can always find a projection to send A, B, C, X to A dash, C dash, A dash, B dash, C dash and X dash that specifies the image of X in a unique way but this particular method obviously specifies the image of X in a particular way. Now the thing is, what we want to do to prove our fundamental theorem of projective geometry is to say, no, we can't have any flexibility about where the image of X ends up. I mean, that's essentially what the theorem of projective geometry says. It says that if you're told how 3 points A, B, C get sent to 3 points A dash, B dash, C dash, then the whole projectivity and the whole way it works on all the other points is already pre-specified. So basically we want to show now that if we were wanting to do another projectivity that achieves the same goals as this, and there clearly are such other projectivities, but if we try to construct the projectivity in a different way, there are clearly a lot of ways we could, string together a load of elementary correspondences to achieve the same goal. But what we're saying is that the kind of mapping which it does, in the sense of what points it sends to what points, is uniquely determined. Let me just say that again in a simpler way. The fundamental theorem of projective geometry claims that given that A, B and C are sent to A dash, B dash, C dash, the image X dash of X is uniquely determined. So okay, let's prove this by reductio absurdum. We'll assume that it's not true, and we'll find a contradiction. So let's suppose instead that there is another projectivity. So the first projectivity we've been talking about, the one we make out of these two perspectivities, let's call that, or three if they're on the same line. But anyway, let's call the first thing we've just been talking about for the last few minutes since the beginning of the lecture. Let's call that projectivity 1. Now let's just suppose for the sake of argument that there was a second projectivity, let's say projectivity 2, which sends A to A dash, B to B dash, C to C dash, and X to X double dash, where X double dash is at another point, a point other than X. So we're making this kind of assumption, which we shall soon find is not correct. We're making this assumption that it's possible that there could be another projection, that there is another projection which sends X somewhere else. Now, why does this lead to a contradiction? Why is this an absurd assumption? Well, the reason is because if you think about that second projection, the one we're positing exists, we'll call that projection 2. Well, projection 2 sends ABCX to A dash B dash C dash X double dash. So that's going to be achieved by a sequence of perspectivities, as projections are. It's going to be achieved by a chain of perspectivities. And so what we can do is reverse the chain of perspectivities. We'll do the inverses of each of them in reverse order, and that'll essentially correspond to a projection which should send us from the points A dash B dash C dash X double dash back to the points A, B, C and X. Okay? So basically I've just said that if there's a projection going this way, there's got to be a projection going back again as well. And then the thing is that we also know that there's a projection from ABCX to A dash B dash C dash X dash, as we've just been discussing at length. And so we can take the inverse of the second projection, which sends us from A dash B dash C dash X double dash to A B C X, and then we can afterwards perform the first projection that sends us from A B C X to A dash B dash C dash X dash, and the composition of two projections is another projection. So what we've essentially done now is constructed a projection which sends us from A dash B dash C dash X double dash to A dash B dash C dash X dash. And now, drum roll, we can use one of our fundamental axioms of projective geometry, in particular the axiom that if a projection leaves three collinear points invariant, then it leaves all the points on a line invariant. Well, that axiom then infers that it must leave this projection from, which essentially supposedly sends x double dash to x dash, leaves x double dash invariant. In other words, to say it simply, x dash has to equal x double dash. So that's pretty much the end of the argument. We have shown that any projectivity, given how the projectivity sends collinear points A, B, and C to distinct collinear points. Whenever I was talking about A, B, and C, and A dash, B dash, C dash, I'm always talking about distinct points, okay? Anyway, we've just shown that any projection which sends A, B, and C on a line to A dash, B dash, and C dash on a line, the way that projection works on any other point on the line, X, the way it sends it to an image is pre-specified. In other words, to put it more easily, it's the fundamental theorem of projective geometry. A projectivity is determined by specifying how three collinear points are sent to three collinear points. It's specified uniquely by doing that. And of course, we can dualize this result as well. So in an analogous way, we have that a projectivity is uniquely determined by how it sends three concurrent lines to three concurrent lines. So a couple of important consequences of the fundamental theorem of projective geometry, which you might want to have a go at proving. In fact, I suggest you do. One of them is that if we have two harmonic sets, then those two are going to be related by unique projectivity. You should be able to see that if you think about how the fourth point of a harmonic set is uniquely determined by the first three. The other corollary I want to mention is that if you have a projectivity that relates the ranges on two distinct lines, well, that's, in other words, it sends points on one line to points on another line. Well, that's going to be a projectivity if and only if the common point of those two lines is invariant. So it's pretty obvious that a perspectivity is going to leave from one line to another, essentially, is going to leave the intersection point of those lines invariant. But it's not quite so obvious that if you have a projection and you know that it leaves the common point between the two lines invariant, then it will be a perspectivity. But it can be shown as it's a fairly fast consequence of the fundamental theorem of projective geometry. Okay, so let's suppose that A and B are a couple of points on our first line, and let's let A dash and B dash be the images of those points under the projection. Now, essentially, what we have then is that this projection sends A to A dash, B to B dash, and E to E. So we have these three distinct points sent to three distinct points. And according to the fundamental theorem of projective geometry, there's only one projection that sends 3 points on one line to 3 points on another line, specifying which triple gets sent to which triple is enough to uniquely define the type of projectivity at work. So basically that means that there's only one projectivity that can do this, and in fact we can create a perspectivity that does this just by linking the line AA dash with the line BB dash. So we found a perspectivity that does it, which is a kind of projection, and we know that there's only one projection that does it. So it must be only a perspective that can do this kind of transformation. Okay then, so if you remember in our build-up to the proof of the fundamental theorem of projective geometry, we essentially were talking about how we could do a projection from 4 points on one line, A, B, C, and X, to 4 points on another line, A dash, C dash, B dash, and X dash. And we were thinking about stuff like, is X dash uniquely determined if we only know A, B, and C, A dash, B dash, A, B, C, and X, and A dash, B dash, and C dash. Now, the thing is that the way that we constructed this kind of projection was essentially to do two perspectives. We used one perspective to get onto this kind of intermediate line, which held the points G, N, M, and Q. And then we did another perspective, to get to that, we did a perspective via center of perspective or origin of perspective A dash. And then we did another perspective via center of perspective A to get from that intermediate line to the final output. Now, the thing is that I think a good question is, could we have used a different intermediary line to do that kind of transformation? I mean, according to the fundamental theorem of projective geometry, there is only one projection that sends A, B, C, X to, well, we don't need to talk about X. There's only one projection that sends A, B, and C on the first line to A dash, B dash, C dash on the second line. However, it's not the end of the story, because in the example we just looked at, we made that projection by joining together two perspectivities. And in doing so, we had to define an intermediary line, a kind of halfway point in our work of transformation. And the question is, could we have used a different intermediary line? And the answer is no. The intermediary line is actually uniquely determined as well. So this brings us to our next theorem, which essentially brings to attention another important object related to projectivities called the axis of a projectivity. So our theorem says that every projectivity that relates the ranges of two distinct lines is going to uniquely determine another special line, which is called the axis of perspectivity. And this axis line is very special in the sense that it contains the intersection of the so-called cross joins of any pair of corresponding points. So what do I mean? Well, let's say that in our projection, A gets sent to A dash and B gets sent to B dash. So the cross join of A, B, A dash, B dash is going to be the place where the line from A to B dash joins with the line from B to A dash. And that's going to be a point, and that point is going to be part of our so-called axis of perspectivity. So if you like, if you want to find what the axis of sorry, the axis of a projectivity. We're talking about projectivities now, let me stress that. I don't know if I said it wrong before, but yes, we're certainly talking about projectivities now. And this theorem basically says that every projectivity from a distinct line to a distinct line has a so-called axis of projectivity. So, well, we've already said if we're doing our perspective like we were discussing before, using centres of perspective A' and A for the two perspectivities respectively, in that case, for another point B, we can see from this old picture that the cross joins of AB and A', B' are going to lie within this special intermediary line, so-called axis of perspectivity. Let's say that we consider the point E where both of these distinct lines meet. Well, in this case has to lie again on this axis. So the only other thing we need to do is to consider what happens in the more general case. So one of the key remarks to help us prove this then is that if we have a triangle E0, E dash, then the axis of projectivity from A, E0, E to A dash, E dash is just going to be this line E0, E dash. So I recommend that you pause the video at different places, look at some of these pictures, do some other examples of your own and convince yourself about these results, because very soon we're going to be using these ideas, especially the fundamental theorem of projective geometry, to prove some really important ancient results. Well, fairly ancient results, like Pappus's theorem is truly an ancient result, a couple of thousand years old pretty much, and also Pascal's result is a very nice gem of antiquity.